The initial climb to cruise altitude will be flown at a constant indicated airspeed. You will already be familiar with variations of this sketch graph. Usually, the illustration uses calibrated airspeed, but for practical reasons, we will be using CAS to represent indicated airspeed. From the elements of principles of flight you have already studied, you will know that air density decreases with increasing altitude. So, in order to maintain a constant indicated airspeed during the initial climb, you must increase the true airspeed. As altitude is increased, the outside air temperature will be decreasing, and therefore the local speed of sound will be decreasing. So, during the initial climb at a constant indicated airspeed, the true airspeed will be increasing, and the local speed of sound will be decreasing. It is obvious, therefore, that the Mach number will be increasing. During the initial climb, an altitude will eventually be reached when the Mach number can no longer be increased without the aircraft exceeding its maximum operating Mach number, or MMO. This is called the changeover altitude. For reference purposes, the changeover altitude is approximately 29,000 feet. The continued climb to cruise altitude must be flown at a constant Mach number, slightly less than MMO. MMO may not be deliberately exceeded in any regime of flight, climb, cruise or descent, to quote the regulations. The outside air temperature will still be decreasing, so the true airspeed must be decreased to keep the Mach number constant. The air density will still be decreasing, so the indicated airspeed will also decrease. You should now be asking yourself how lift can remain constant if both air density and indicated airspeed are decreasing. When climbing above the changeover altitude at a constant Mach number, the angle of attack must be increased. We have now reached the tropopause, above which the outside air temperature remains constant in the international standard atmosphere. Because outside air temperature remains constant above the tropopause, to maintain a constant Mach number, the true airspeed must remain constant. This fact is not obvious when asked a question about it, but the ability to visualize this diagram will help. Because air density is still decreasing, the indicated airspeed will continue to decrease, but at a lower rate, because during this portion of the climb, the true airspeed is constant. We can now consider the changes that take place in a descent from cruise altitude. Unsurprisingly, the initial descent will be made at a constant Mach number. Initially, the true airspeed will have to remain constant because of the constant outside air temperature. And because of the increasing air density, the indicated airspeed will be increasing. But now, to keep lift the same as the weight, the angle of attack will have to be decreased. As the tropopause is passed, the true airspeed will have to be increased, and the indicated airspeed is increasing at a greater rate because both the true airspeed and the air density is increasing. As the changeover altitude is approached in the constant Mach number descent, the aircraft is now in danger of exceeding the other maximum operating speed, VMO. In case you've forgotten, VMO is an EAS, the only V-speed that is not a calibrated airspeed. As with MMO, the regulations state, VMO may not be deliberately exceeded in any regime of flight, climb, cruise or descent. So the descent below the changeover altitude is carried out at a constant indicated airspeed, with true airspeed and Mach number both decreasing. This diagram contains all the information you need to answer the relevant questions in the written exams, so it's a very good idea to commit it to memory. It was explained earlier that as the shockwaves form at aircraft speeds greater than m-crit, the centre of pressure moves rearwards. If we view the aircraft from the side, we can see the result of this event more clearly. An aircraft nose-down pitching moment is generated, which is called Mach tuck. Mach tuck is the first physical manifestation of shockwave formation on the aircraft. When studying longitudinal stability, we learned that an aircraft must require an increasing push force with increasing speed. Mach tuck must therefore be opposed with an automatic aircraft system called Mach trim. In practice, Mach trim generates an opposing pitching moment as the aircraft accelerates to, as the examiners word it, high Mach numbers. In fact, Mach trim must generate an opposing pitching moment which is greater than Mach tuck. This illustration will show us why. All aircraft must have a stick force gradient that requires an increasing push force with increasing speed. At high Mach numbers, Mach tuck reduces the stick force gradient to a negative value, which means an increasing pull force would be required. At high Mach numbers, Mach trim has to generate a larger pitching moment than Mach tuck to ensure the required stick force gradient is maintained. We can now consider how Mach trim is achieved. There are three methods. Move the elevator up, decrease tailplane incidence, or move the centre of gravity rearwards. However, the preceding three methods of achieving Mach trim will only work while accelerating beyond m-crit. It is more correct to say that Mach trim adjusts the longitudinal trim at high Mach numbers. m-crit has already been defined as the aircraft Mach number at which the local speed of sound first reaches Mach 1. Let's see what happens as the angle of attack is increased. Because of the reduction in cross-sectional area of the airflow, the boundary layer has accelerated, and instead of a local Mach number of 1 at an aircraft Mach number of 0.75, the local Mach number has increased to 1.05. So, Mach 0.75 is no longer m-crit. The increase in angle of attack has resulted in m-crit decreasing to Mach 0.7. The significance of a decrease in m-crit with increasing angle of attack will greatly influence the safe operation of jet aircraft operating at their cruise altitude. You might like to think about what would require an increase in angle of attack in the cruise. It was mentioned earlier that at speeds above approximately Mach 0.4, the 1g stall speed starts to increase. We will now take a look at why this happens, and the effect it has on the aircraft when cruising at high altitude and high Mach numbers. The illustration shows the effective airflow starting to upwash as soon as the leading pressure wave passes over it. We can also see the average effective airflow angle of attack. As the Mach number increases, the effective airflow has to upwash through a greater angle, and the effective angle of attack will increase. The result will be a decrease in CL max and a reduction in stall angle. We know that air density does not affect the 1g stall speed, and we know that airflow separation just before the 1g stall can cause airframe buffeting. To avoid any confusion, we should now call this low-speed buffet. Low-speed buffet will begin at a speed called the buffet boundary. We can say that as altitude increases, the 1g stall speed is constant until a very high altitude is reached, above which the stall speed increases. There is an altitude above which flight at the 1g stall speed should not be attempted. This is called the aerodynamic ceiling, at which only one speed is possible. You might think that in the cruise we do not operate jet aircraft anywhere near the 1g stall speed, but we have just seen that increasing Mach number makes the 1g stall speed increase. When operating a jet aircraft at high altitude and high Mach number, it will be necessary to turn occasionally for navigation purposes. We already know that turning requires lift to be increased, and therefore the load factor will increase. We also know that increasing the load factor will increase the stall speed. With increasing load factor, the so-called very high altitude above which the stall speed increases will get lower and lower and lower and lower. The dashed blue line represents a constant Mach number. You can appreciate that when turning at high cruising altitude at high Mach number, the bank angle must not be excessive. We can now superimpose a line representing the EAS at which high-speed buffet will occur. High-speed buffet is caused by the excessive airflow separation from immediately behind a shock wave we saw earlier. High-speed buffet is a Mach number phenomena, but a given Mach number will represent a decreasing EAS with increasing altitude. There will also be a high-speed buffet boundary above which buffeting will begin. So there is low-speed buffet and high-speed buffet. A low-speed buffet boundary and a high-speed buffet boundary. At low altitude, there is a wide operating speed range between the low-speed buffet boundary and the high-speed buffet boundary. But with increasing altitude, the operating speed range with no buffet decreases. This is the operating speed range envelope at sea level. Stall boundary on the left and high-speed buffet boundary on the right. At a representative cruise altitude for a jet transport aircraft, the operating speed range envelope is much reduced. The standard definition of the aerodynamic ceiling is the altitude at which the low-speed buffet and the high-speed buffet are the same speed. The aerodynamic ceiling can also be referred to as coffin corner. We can now consider how low and high-speed buffet can be avoided while operating a jet transport aircraft in the cruise. We will now see how a jet transport aircraft can be operated in the cruise at high Mach number without the risk of buffeting. This is an example of a buffet onset chart, with emphasis on the word onset. An aircraft must be operated at all times with a margin of safety from the onset of buffeting. All we have learned so far about the factors that affect Mach number and shockwave formation are drawn together in this chart. In particular, we have learned that there is an altitude at which only one speed is possible, the aerodynamic ceiling. It would be extremely foolish to fly at this altitude, because turning to a new heading or the slightest turbulence would stall the aircraft. Regulations, if not common sense, require an aircraft to be operated with a minimum margin to the buffet of 0.3 g. This equates to something called the 1.3 g altitude. We will now examine the buffet onset chart in detail, and then derive some operational data from it. On the left, we have pressure altitude, increasing vertically downwards, labelled as flight level. At bottom left, increasing to the right, is Mach number, with MMO highlighted. At bottom right, above the axis, there is bank angle increasing to the right. The calculation for load factor has been done for you, and is listed below the axis. Increasing vertically on the right, we have aircraft weight in tons. The plots on the left represent the onset of both high and low speed buffet at a series of flight levels, with flight level 350 highlighted. So we can manipulate the data on the buffet onset chart. We'll zoom in. Aircraft data will be presented to you. The aircraft is flying at Mach 0.8, at flight level 350, at a weight of 110 tons. You would move upwards from Mach 0.8 to flight level 350 and across to 110 tons, and then down to the load factor bank angle data, where you would find that the aircraft will start to buffet at a bank angle of 53 degrees, or a load factor of 1.65 G, at a higher altitude of flight level 370. Buffet onset would be at a bank angle of 49 degrees, or a load factor of 1.46 G. If we consider a lower weight of 100 tons, a bank angle of 57 degrees, or a load factor of 1.81 would be possible at buffet onset. We'll revert to the original data, so we can determine the 1.3 G altitude under these conditions. Move upwards from 1.3 G to 110 tons, and left to Mach 0.8. Now interpolate between flight level 390 and flight level 410 to discover that the 1.3 G altitude is flight level 400. If you are asked if the 1.3 G altitude can be exceeded for any reason, the answer is no. The 1.3 G altitude may not be deliberately exceeded for any reason. The last thing we will determine is the speed of buffet onset in 1G flight, at both high and low speed. This is a common written exam question. Move upwards from 1G to 110 tons, and left towards the flight level 350 plot. We can see that the high-speed end of the flight level 350 plot is above our position on the graph. This tells us that under existing conditions, high-speed buffet is not limiting. The high-speed limitation is MMO. If we continue to the left, we will eventually intersect the low-speed end of the flight level 350 plot. Moving downwards, we will discover that the aircraft would begin to low-speed buffet at Mach 0.57. The conclusion is that under existing conditions, high-speed buffet is not a problem, and the maximum speed of the aircraft is limited by MMO, the maximum operating Mach number, and the aircraft would begin to low-speed buffet at Mach 0.57.